Yes, thank you. Yeah, I thank Radu, but Yuri had to leave for the invitation. It's great to be back in Vienna. The workshop is wonderful. I don't have too much to say, so I'm just going to take a few minutes. There's something else that happened a couple of days ago when I arrived. They took my photo in this room. And then, you know, there's this window pane where they put people's photos. And they put my photo next to Terry Rockefeller's. Okay? It's, I interpret this as a celestial sign that the rest of my career is going to take off. Whatever remains of it. Okay, second remark. This last name has been baffling audiences for many years because there's an I here without a dot. You see? That's a specialty of the Turkish alphabet. And it's not an I. Okay? So most people pronounce my name Pinar. But my name is not Pinar, really, because in France, there's this word in French, which means cheap red wine. Okay? So, this is not my name. So, okay? So please, let there be no mistake about this. Okay. So after these two unnecessary remarks, let's let's go back to this boring things. Is this not okay? Pinar. It's like this this sound is squeezed between the P and N. Pinar. Okay, it's like it has to just come out of your mouth in one shot. It's not Pinar at all. Please.
What does it mean?
It means fountain, water fountain, or in Italian it's sorgente. I don't know, fontaine in French. Sorry, it's the meaning. It's really the meaning. So I have two co-authors. Buse is a former student who is now at EPFL. Deniz is a current PhD student. This is the outline. Everybody knows this idea here. You want to limit the number of non-zero components, and this has been this is the bread and butter of compressed sensing and lots of other things. But perhaps it is not. It has been part of portfolio selection, but perhaps not so much as these other areas. So we'll have to deal with this function as zero. This problem, of course, is very hard. So this will be another demonstration that it's a hard problem. Okay. So okay, modern portfolio theory built around mean variance, a theory of Markovitch. There are ways of putting this problem. There is maximize the expected return subject to control on the variance, or vice versa, or you put them into an objective function together with a weight. All these things can be shown to be equivalent in the end under certain conditions. So this goes back to 1952 to Markovitch, and I have been told that when he first presented this at the University of Chicago, they rejected this as not worthy of economics. Then we know the rest of the story. It's, anyway, so let's go to the problem. So this is what we want to do. We want to solve really. I'm not putting any non-negativity restrictions on X for reasons that will become clear in a moment, because that would make the problem even harder. But anyway, so this is the variance covariance matrix of the returns. This is target return R bar specified by the investor. This is an estimate of the mean return of these assets, and X are your variables, so in capital N assets, and these are your portfolio positions. So we allow, by allowing X to take negative values, we allow what is called short positions as well. Okay, so this is the problem, CP MVP, and you could pose this problem as as an integer optimization problem, but with a quadratic objective function. So, and this beta is a positive parameter that controls the sparsity of the portfolio. Okay, so this problem was studied, as far as I know, the first one, but perhaps there were people before, by Bienstock. This name should actually have been Bienenstock, but I don't know, somehow. Sorry? But it's not Bienstock, it's Bienenstock, which means a beehive in German. But so, so somehow his name has been obliterated. So what we are going to do, we are going to analyze the structure of minimizers of this problem on the left, and show existence and uniqueness of global optimal portfolio. Of course, I'm not going to go into the details of any of these things. Okay, then a lower bound for a globally optimal portfolio, an upper bound on the infinity norm of a globally optimal portfolio. Then we'll we'll leverage some of these results to develop a implicit enumeration type algorithm with coupled with a heuristic. And then I'm going to compare this to MOSEC. You might ask why MOSEC? Because Groby doesn't work. Okay, and MOSEC seems to do at least something. Okay, this is not to claim that we are better than MOSEC or anybody else. It's just to benchmark what we get at the end. Okay, so I should mention here Bulgarian-French mathematician Nikolova. So we built this work on her work, not on portfolio optimization, but other things. And she died, I think, a couple of years back. So I thought I should mention her name. Okay, so some notation. This is just to put things correctly for a support set omega. Actually, for sigma or omega, you just extract the subcomponents of these vectors and matrices. It looks horrendous, but you have to do it. There is the inverse operator, which is z omega, which takes a vector with non-zeros and then puts zeros into coordinates and maps it into a vector with some zeros in it. So these are all needed to write things appropriately. Okay, so we define the following sets. We have the entry-wise norm of matrix D, and the objective function we denote by this f beta. So it's a function parameterized by this beta here. Okay, so this x omega is when you restrict the support. In other words, the non-zero components to the indices in omega. Okay. All right. So now you have this standard assumption the expected returns are different, and they are not. None of them are equal to the target return, the standard assumption in portfolio theory. So if you restrict the support to omega, this would be the problem that you would solve. Okay, and you can rewrite this problem, this restricted problem, in this form as well. They are equivalent. This is a simple observation. So this problem is a convex optimization problem. You have affine constraints, so you can just solve this problem in closed form. This is well known, of course, in every book on portfolio theory or mathematical finance. It's there. So there's a closed form formula. Okay, but what is interesting is that for any support that you choose, in fact, you can show that the solution to this problem, since D is, perhaps I forgot to say, D is assumed to be positive definite, so there is a unique portfolio. And this, in fact, can be shown to be a locally optimal sparse portfolio. Okay? And conversely, a locally optimal sparse portfolio is always the solution of this subproblem without the L0 term. Okay, so now we can also prove a lower bound on the entries, on the absolute values of the entries of a globally optimal portfolio, okay, with support sigma hat. So you can show that the absolute value has to be at least this much. By the way, this notation, it's non-standard. It is the square root of D in the sense of matrix square root, not component-wise square root. Okay. Now, there is this annoying term here. Everything is computable here except that this annoying term, but we can replace this by the 2 norm of the matrix D, but this bound is loose. But it's easier to compute, and this is what we are going to use in the algorithm. So another result is upper bound on the infinity norm of a globally optimal portfolio. This is the smallest eigenvalue of the matrix D, the variance covariance matrix. This is again computable, easy to compute, and you can use this upper bound if you solve the MIQP formulation, because the MIQP formulation needs this big M. So all right, now so far I didn't assume that there was a riskless asset in the asset universe, but usually there is the bank account or a government bond, which is assumed riskless, not exactly riskless, but anyway, so not like the assets. And in this case, the problem changes a little, and we'll make provision for the position in this riskless asset. Okay. Again, under the assumption that we can take a short position. In other words, we can borrow from the bank. So if it's a short position, you can borrow money. Okay. So the problem changes a little after elimination. So now there is a single constraint left. Again, there's a standard assumption that this riskless rate is not equal to the expected return of any of the other assets in the universe. And then you can again prove this, it's a necessary condition. You can prove this lower bound on absolute values of the non-zero position in a globally optimal portfolio. By the way, this bound is tight, and this term warm start is perhaps not appropriate, but I don't know how to name it otherwise. Like an advanced start heuristic that I'm just going to tell you more about in a second. Okay, so it's similar, but requires a proof from scratch. This anyway. So again, you can prove an upper bound on the infinity norm of a global minimizer or global portfolio. Again, this bound is also tight. But it wasn't tight in the absence of the riskless asset, which I haven't told you, but now I'm telling you. In the previous case, it wasn't. But here it is tight. We have an example. For the other, it need not be tight. Okay, now existence of globally optimal portfolios. So we want to prove that this set of minimum globally optimal portfolios is non-empty. And here comes Mr. Tobul into the picture. This is the book by Freddy Oslander and Mark Tobul. So we use a result of these two gentlemen to show that this set is not empty. Okay, I skipped the horrifying details. And yes. Right, but okay, so there is a problem. There are too many of these locally optimal portfolios, exponentially many. So to do computation, what are we going to do? We do a branch and bound type algorithm, but we couple it with sort of heuristic. Heuristic because we don't use the true bound. You replace this norm computation by something loose. And this is an idea to eliminate from the asset universe those assets which most likely will not be in the final globally optimal portfolio. Okay, but of course this may not always work. So that's why it's a heuristic, because we don't use the exact bound. Okay, and then at each iteration, we have two subproblems in which we choose an asset J to include to the support or to exclude from the optimal support. Okay, so left and right nodes at each node in the tree, and we compute lower bounds and upper bounds, and this is very heavily simplified pseudocode. This is horrendous to explain, but I will skip it. So it's in fact just a regular branch and bound, and we start eliminating first some indices, and then we start the branching and bounding process. Okay, so let me skip this and go to some of the results. So this is real data. Euro bonds, world bonds, Nikkei 225. So this is real market data. S&P 500. This is the largest set of assets. Okay, and of course we estimate this variance covariance matrix and the expected return from these. Of course, this is subject to error, which we shall address in a subsequent paper, not this one, because. Okay, so some results with compared to MOSEC. Okay, so this is for Euro bonds and world bonds. These are not too big, right? And here you already see. So these are the choice of beta, and the sparsity of the. Well, when I say sparsity, again, it's a misnomer. It's the non-zero elements in the final portfolio. Yeah, it's in seconds. Yeah, CPU time in seconds. You see already MOSEC blows up. Okay. This is the error of the solution that we report compared to the. So it's the error of my solution with respect to the MOSEC reported solution here, mosaic could not yield anything. Similar picture here, okay? And these are not large problems. So these turn out to be really difficult problems for mosaic. Okay? Maybe we should turn them into a test problem library for MIQP solvers. Yes. Yeah. Sorry? This is the elimination at the beginning. We eliminate 30% of the assert universe, etc. Okay, so this is no. No, I don't think we do. Might be a good idea, yes. Perhaps we have tried. I'm not sure. I will check this with my coworkers. I don't. Sorry? Yeah. Happens. So next, where we have bigger data sets. Okay. So again, a similar. No, but now you see when mosaic is able to solve, we have an error of 12% in these two problems. So what we have computed here is 12.5% away from mosaic optimal solution. So our elimination did not give us the optimal portfolio. But of course, the CPU of mosaic is just enormous. Okay, something similar here. Okay, but here we don't have anything to benchmark against. Now, in the next table, I'm going to show you when I limit the computation to 1 hour. Okay, when I do this to wall clock time, then the bold numbers with a negative sign is when we are doing better than mosaic with respect to the final solution that we report after 1 hour. Okay, and when there is a positive number, mosaic is doing better after 1 hour. It's a mixed picture. But when we do well, we do really well, and sometimes mosaic does really well. So there is still work that needs to be done in this algorithm. But as a first attempt, it gives mixed results, but sometimes it really works well. This is like a efficient frontier, but it is three-dimensional because you have two parameters: the target return and the sparsity controlling parameter. So some other time behaviors, okay, of CPU time and wall clock time. And I'm almost ready to finish. So what, just to recap, we gave an analysis of local and global portfolios. We use some of these ideas for, in fact, this, I told you that this upper bound can be used for MIQP, and we tried this, although sometimes it helps, sometimes it doesn't. In other words, just putting blindly a big M, perhaps sometimes it works better. I have no idea why this happens with mosaic. Okay, so we have the existence result, and we have a branch and bound code that sometimes works very well, sometimes it doesn't work so well, but that's branch and bound. Thank you. That's all I have to say.